So we're looking at a little problem that looks like this. If you're online, it's in Moodle. It's called the Torsion handout right there. Okay. So we'll just finish up torsion with this one. So what we're going to do with this thing is we are going to have a shaft that's run by a motor, and we're going to push down on a plunger, okay, like that. And we need to push the plunger down. And we need to design the shaft so that it can do that. Now what's going to happen is that plunger is going to push back on the shaft. And it's got quite a lot of force. It's going to push up with 4,000 newtons is what it's going to do. Okay. So now that plunger is vertical, so the force it exerts is vertical also. So that'll be 4,000 newtons pushing up. All right, now when that happens, we want the shaft to meet some criteria here. We want the maximum allowable shear to be 5,000 psi. So the shear cannot be more than 5,000. Okay, we can't have that. We have to push the plunger down 3.464 inches right here. So that's as far down as the plunger has to go. Now the motor rotates the shaft 2.275 radians per second. That plunger has to move down 3.464 inches in 2 seconds. Okay. So that's the criteria basically, 5,000 psi, and it has to push that plunger down 3.464 inches in 2 seconds. We've got the angular speed on the motor side is 0.275 radians per second. So what we want to do for starters is find the minimum shaft diameter that we can use that will do this job. Okay? So we good with that? Do we have any questions on that? Okay. All right. So why don't you find somebody you could work with, a couple, maybe 3 people. I know it's hard in this room, but find some people that you can work with. And let's start by finding things. So let's find the torsion first. So what's the torsion in the shaft? Check in with me here. If you're online, I'm going to pause the recording because there'll just be a lot of silence and no reason for that. So if you're online, pause the recording, try and find the torsion in the shaft, and then we'll check back in after you've done that, okay? All right, if you're looking at this and you're online, we've got torsion is force times distance. The force is just a force. The distance is the distance to the center of the shaft. What I've seen from a number of people, or some people, was that equation right there, which is definitely on the right track, but it's not quite right. It's on the right track, though. What's the problem there? Let's kind of imagine what's happening at that plunger. You're going to have a bearing in there of some type, right, to hold that plunger in? I mean, you just can't be pushing on something like that. Something's got to hold it in place. And I'm not talking about just the downward movement. It's the movement to the side. Because if you just pushed on that thing, as shown, you'd push the plunger to the right, wouldn't you? With me there? But so you need some sort of bearing in there to hold it. Because if you don't, that whole plunger will get pushed that way. Well, that's not going to happen. So I do think we've got 4,000 doing that, but I also think on account of that bearing, we got a force like that. So what we're going to end up with, I think, is a force like so. You all with me there? Okay. So we're going to have to account for that, and that's very much a function of the angle. We're going to assume that that force is perpendicular to that plate that extends out. So why don't you work with that and see what you can come up with for the torsion. As I was saying, this is very much on the right track. It just didn't really account for that little trigonometric angle thing that's happening there, okay? You good with that? Questions? Okay, I'll pause again. So what we got going on there, we got an inverse tangent, arctan 3.464 over 6. And that's pretty darn close to 30 degrees. Good? Okay. Now, given that, see what you can do with the torsion. So see if you can find the torsion next. What's the torsion that would be caused? You might have to do some trig here yet, okay? So be thinking on that. Look at the moment arm, look at some of the different things that are happening here. You might have to do some trig to get this worked out. Okay, so the deal with this one is you really got to watch your trig. The 4,000 is a vertical component of the force. So what you got going on there is you have two components of the force. You got 4,000. You've got the resultant force like that. And then you've got a second force doing this. All right, and you know that's 30 in there. So I think the thing to do here is to realize that if you take FR cosine 30, that equals the 4,000. See, the resultant has to be bigger than 4,000. Okay? The intuitive thing people often do is take 4,000 times cosine 30, but that'll make your resultant vector smaller than 4,000, which isn't right. The resultant vector is bigger, so it'll be 4,000 over cosine 30. That will get you that resultant force, which is perpendicular to the moment arm, so you need to also get that distance there, and then do the torsion as force times distance. Okay, so you should be coming out with about 32,000 when you do that to get the torsion. 32,000. Okay, so both of these numbers, as it turns out, using those methods is wrong, and you should end up with 32,000 after you do that. So just take a minute, see if you can get that. I don't want to hang up too much on this because I want to get more into the torsional aspects of it, but that was a little tricky. It does use the FD idea, but you have to really watch the trig on that. There's some things you have to think through on that one that are a little tricky, admittedly, okay? All right, so we're going to get the force, which I think is about 46.28 or something, and then the distance, 6.928, I think, just speaking from memory, I don't remember, but multiply those together. So you need and get the torsion. So the torsion is the force times the distance, and that should come out to be 32,000. Now the distance is the hypotenuse distance. So to get the distance, you do the square root of dx squared plus dy squared, and then to get the force, you're doing 4,000 over cosine 30. I think that's what we want. And then we should get to the 32,000. Now, once you've got there, this is stuff that we've looked at a little bit before now, once we get there, because you've got two criteria. One is very direct. It's what the shear is 5,000 psi. You should be able to figure out the radius required for that. But what's the other criteria you have for when we analyze shafts? What are the two main things we look at? Yeah, the angle. So what we have here is the shear stress, like so, and then we've got the angular formula, like so. All right, that's basically how you analyze a shaft right there. And those are just basic equations off the formula sheet. They're at the top of the stack on that. So that's formula 91 and 93, okay? Now, you've got tau max, so you should be able to back into the radius for that. We did that in class. We did some homework based on that too. Now, the phi bit is a little tricky because I didn't say phi is such and such. I didn't say that. But you have enough information there to figure out what phi is. So why don't you look at some of this information and see if you can come up with phi based on it. And this is something I'd like you to understand is what is that? You know, what is the twist in the shaft? And I've given you enough information to find what I would call the allowable twist in the shaft and see if you can come up with what phi is next, okay? I think, you know, once we get down to knowing what tau and phi is, you know, the torsion, you can plug this stuff in and solve for the radii, I think. But let's kind of focus next on what is phi. Given the information presented in this handout, what is phi? Okay, so let's look at that next. All right, so when we look at that, look at the difference between what the shaft twists at the motor versus what the plunger must do in 2 seconds. That's the amount of twist you can have on the shaft. If you look at it in a simple sketch, let's start with a horizontal line that's kind of collinear with the plate. That's got to be 30 degrees here. Look at what the back does. It's more than 30 degrees, right? What you want for the twist angle is the difference. That's how much the shaft can twist, and it'll still do the job. Okay? So that's the twist angle. All right? So I'd like you to do this for Friday. We can go over it a little bit tomorrow too, all right? I'll try and get you a test review tomorrow. It looks like the exam will be a week from Thursday. And that will be the 27th. That's what we're looking at Thursday. Okay. So this will be due Friday. Okay, we'll go over it a little bit tomorrow too, but this problem will be due on Friday.